I want to go back to I want to go back to the handout that we've been working through, and there's another handout, but you may not be able to find it in Canvas, so I'm going to kind of modify what we do on Friday. It'll be kind of a combination of review and then a new topic, and then hopefully on Monday we'll be able to just keep it pushing. So let's see. I think we stopped here. Did y'all get a chance to watch the video that I sent on yesterday? Um, and if you did, if you wouldn't mind sharing some feedback, whether or not it made sense. All right, so I think we left off talking about this other isomer and the stereo centers that are here. So I want to kind of walk back through this. We already resolved the first stereo center. We said it was S. And let's do the other three. But I'd like for someone to volunteer to do each one to give the configuration. And let me see something. Clean this up. As we've already established that the sp2 carbons and the rings and the carbonyls and all that are not chiral centers. We've already established that. And we've already did this one right here. So we got 4 chiral centers. And I'm going to copy this and put it on a blank page so we can work through it and work through some other information. All right. Do we have a volunteer to take the second stereo center where the hydroxyl group is?
Are we labeling priority?
Yes. So let's prioritize it and then determine the configuration. Yes, let's do that.
Okay, where the hydroxyl group is, the oxygen would be 1.
Okay, so that's 1. Okay, good.
And then the second one would be the carbon connected to the nitrogen.
Okay.
And the third one would be the carbon connected to the other carbon.
Right there.
Yeah.
Okay, great. And then where's the hydrogen in this case?
The hydrogen is going backwards.
It's already pointed back.
So it's gonna you don't flip the rotation, so then it would be that's clockwise. No, that's counterclockwise. So then that'd be sinister.
Yes, that's right. Good.
Okay.
Excellent. All right. What about the next one? Can we have somebody do that one? This is another one where H is already back.
I can do
Come on.
it. So the carbon with the nitrogen on it is the first one, or the nitrogen.
Nitrogen, yes. Good.
And then the second one is the one nearest to the OH group.
Okay, here.
Yes. And then the third one's the one with the ring on it.
Okay. All right. So let me highlight that. So is that counterclockwise?
Yes.
So that's also what?
S.
Yes. Good. Excellent. I'm glad y'all are catching this. What about the last one? We know nitrogen is going to be 1. And then 2 or 3 is going to be either this carbon or that carbon. Now this is a different type of branching. So the carbonyl is actually going to take precedent here, not the isopropyl group. All right. So if the carbonyl is 2 and this is 3, what is the configuration?
R. Oh wait,
That's counterclockwise, isn't it?
it's S.
S.
So that's also S. Right. So all 4 stereocenters in this molecule are S. Here's the question. How many, we already talked about this, how many stereoisomers are present or possible? How many stereoisomers are possible? What's the formula again?
It's 2 to
2
the
to the
n,
n.
so it'd be 2 to the 6, which is 64. Or 4.
But we only have 4 stereo.
Four
So
on
N
that
is the number of stereocenters, yeah. So that would be what, 16?
Yes.
Possible. Okay, great. Now, if this original image is S, 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 right? That's all 4 stereocenters. What would the configurations be in the enantiomer for those same stereocenters?
R, 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 R.
Good. Excellent. That's exactly right. Everything gets reversed in the mirror image. Okay. What about if I ask you to give me 1 diastereomer? Starting with that.
You will only change one, right?
That's exactly right. So pick, which one do you want to change? Does it matter?
I don't think so.
It doesn't. You can change any one of them as long as you only change one. So we'll say R, S, S, S. Is that making sense?
Yes.
Mm-hmm. What would another diastereomer be?
R, S, R, R.
Say R, S, R. That's too many. Unless you're talking about a diastereomer of the enantiomer. So yes, let's do
I was
that.
looking at the wrong thing.
No, you good. You good. Because that enantiomer would have a diastereomer also. So we could say R, S, R, R. That would definitely be one. And you can consider each one of those, the original image and the mirror image, changing 1 stereocenter at a time to get a diastereomer. So at least 4 diastereomers from each one, right? So with that being said, the point of all this is to understand in the enantiomer, all of your stereocenters change, right? And the diastereomer, you only change 1 at a time. All right. Any questions about that? So let me do this. Let me go back and get the original. So I want you to see this kind of and take this and capture it. All right, so if I took this, right, then the enantiomer would look like this, where this would now be wedged, and I know I'm cheating, and this would be dashed, and then so with this and that. Is that right? Right, compared to the original image here, right? If it's the enantiomer, we already said everything would be different. So all of your stereo centers would be inverted. All right. Let's do a right. If it was just a diastereomer, then we could just change this and leave the rest of the stereo centers the same. Can y'all see that? So we added to that one, but everything else stays the same. All right. Questions about that? I have a question. What would the configuration be here? Right? If up here we said it was S, this one, we said that was S. If I change that in the diastereomer, what would it be if I made it wedged instead of dashed?
R.
It would be R. Right. And then the rest of these, I haven't. Oh, sorry. That's the wrong one. Sorry about that. That would be R. The rest of these I haven't touched. So this would be one of those diastereomers, right? Where, again, you change one stereo center and you leave the rest. In the enantiomer, it would be everything, right? Right. Any questions about that? Or about
Would
anything
it
we talked about?
would it still be stereomer if you change two and left it two?
It would be a different type of isomer if we change two of them.
Okay.
Yeah, it would be a different type of isomer. It would no longer you would no longer call it a diastereomer in that case, but it would
Okay.
still be a stereo isomer.
All right.
Good question. All right, other questions? All right. I didn't send this the video for reaction, stereochemistry and reactions, so I don't really want to touch that. But what I do want to do is work through a couple of examples or allow you to work through some examples. There's a handout that was on Canvas that you may or may not be able to access. So what I'm going to do is grab it and upload it to the chat. And we're going to work through some of those examples. And I'll display it, but I'll upload it to the chat for you to have in your own possession. So give me a second so I can log in and download it. So how many stereo centers are present? You're right about that. Find the number of chiral centers. You're right. How many chiral centers are present in that molecule in number 3?
One.
Three.
There are 3 total.
Um,
So there's one here, and one here. Can y'all see my cursor?
Yes, sir.
oh yeah.
Mm-hmm. So that means that how many isomers or stereo isomers are possible?
Wouldn't you do 2 to the end?
8.
Mm-hmm. 8 total. Good. All right. So one of those stereo isomers is going to, at least one of them is going to be what? Is it going to be the mirror image?
Mhm. Yes.
So what would that look like? Let's draw that. Y'all bear with me with this touch screen. Would the mirror image look like this? Is that right? Where everything changes?
Yes.
Wouldn't
It's
the mirror
just
image
I'm
have?
confused.
Go ahead, I'm listening.
And I get confused when I thought that everything was supposed to be also flipped on the other side, like the chlorine should be on the other side.
Well, okay, that a good question. Oh, good catch. And you could really draw the mirror image one or two ways. You could draw it such that there's a mirror plane here, right? And then the molecule is facing itself, or I could just turn it over, right? So the way I have it drawn is I just took all of the stereo centers that were there and I just altered them. So instead of that carbonyl being on a dash, now it's on a wedge. Instead of the OH being on a dash, it's on a wedge. And then instead of the chlorine being on a wedge, it's on a dash. Because we all agreed that the mirror image is the absolute opposite of the original. Everything changes. Is that right?
Yes.
Mm-hmm. So that's why I have it drawn that way. Does that make sense?
Yes.
Okay. So that's the original image and the mirror image. Now, tell me how I can get at least 3 more stereoisomers from that original image. What can I do? What can I do to get at least 3 more images, 3 more stereoisomers from that original image?
Don't you rotate it to like change the R and the S?
Well, am I rotating it or can I draw diastereomers of it? Isn't that right? I could take the original and make a diastereomer by altering one stereo center.
Yes.
Yeah.
Could I do that? Let's see.
You can change one dash line to a solid.
Mm-hmm. And leave the
Uh-huh.
rest, right?
Yeah.
Let's do that. So I'm going to change this one. This is terrible. Sorry. It's not terrible. It's just me. So that's that. And then I'm going to leave these two the same. Is that right? That's a diastereomer of that original image, isn't it?
Yes.
Mm-hmm.
Can I draw another one? What would you do to draw the second diastereomer? I mean, we already at 3 images and we said the total was 8, right? What would you do to draw the second one?
We could change the OH dash line to a wedge line.
Leave the other two the same, right? Is that right?
What'd you say?
Leave the other two the same?
Yep.
Yeah, exactly. So let's do that. I'll get better with this touch screen. This is weird. But it's convenient though.
Excuse me, Dr. Russell.
Go ahead.
When you change a wedge to dash and then vice versa, can you only do one per per?
Diastereomer?
Yes, sir.
Yeah, you only change them one at a time.
Okay.
So which one are we changing? The OH? Is that right?
Yes.
And this stays, right? Right? And we can do it again based on the original, can't we?
Yes.
We'll just change the chlorine. So we'll do this. Now this is here. This is here. Like that. And then this is here. Okay. That's a total of what? 1, 2, 3. That's 5. Is that right? That's 5 total stereoisomers, including the original. Now, where does the where would the other 3 stereoisomers come from? I'll buy lunch for the first person who can tell me that.
The mirror images of the diastereomers.
Just look at God. You're exactly right. The mirror image, every one of those diastereomers is going to have a mirror image, right? So it's going to have an enantiomer. And that's how we get to those 8 stereoisomers, right? So I want you to work on that, drawing those mirror images of each diastereomer. How would you do that? Right? You could do it one or 2 ways. You could put a mirror plane in and reflect it, or you can just change all the stereo centers in each one, right? And either way, it's a proper way to illustrate the mirror image. Let me email this right quick. I'm sorry. I need to attach this handout. Sorry about that. Let me find it. Come on. All right, this is I'm sending this out as an announcement with the attachment. That way, anybody who put your name in the chat, rather than me emailing you individually, you should get it in an announcement. So, because that'll save a lot of time. All right, questions? Any questions about that? Any confusion? It's different. It's different when we actually put our hands to it in this way.
Excuse me.
But these examples are a lot less complex than what we've been looking at. So the concept and the idea should carry.
Excuse me.
Go ahead.
Could you do an example of a mirror, of one of those becoming a mirror image, please?
Oh, absolutely. Which one do you want to take?
The one on the farthest to the right.
Farthest right? Okay. So let me zoom on that. Let's see. All right. let me pull up my annotation again. So the one on the far right, well, everything is dashed.
Yes, sir.
All right. So the mirror image of that would be here, where instead of everything being dashed,
Everything is wedged.
they could be wedged. That's exactly right. All right. So that'll be that. That's that, and then that's that. Right. This is the mirror image of that. You agree with that?
Yes, sir.
And it'll be the same for the other two. All you do is, if it's the mirror image, the example we just looked at before I switched over to this, we said in the mirror image, if the original is R or whatever, then the mirror image is going to be the exact opposite. It'll be all S. It's the same thing here. If in the diastereomer that we had shown, if everything was on a dash, the mirror image, all your substituents, all your chiral centers are going to be wedged. They're going to be the exact opposite, right? So although these are diastereomers, each one of those diastereomers has an enantiomer. It has a mirror image. Oh, who was that gave me the answer to that question? I couldn't see, but put your Cash App in the chat. All right. Any other questions about that?
Yeah, I have a question.
Go ahead.
So basically to get the mirror, we're just flipping the dashes and wedges. But you said we could also like draw a plane and literally reverse it,
And
right?
reflect. You can draw a plane and reflect it. Like if I took let's say if I started with the original image right here. This is dashed. That's dashed. That's wedged. That's chlorine, OH, and aldehyde, right? I could draw a plane here and just reflect that. You see? Like it's looking at itself in the mirror.
Right.
Following?
So
So none of that, I won't change anything if I draw it that way. I have to leave it. Because if you change it, when you flip it over, what happens is everything will end up being the same. Right?
right. So either way could be correct.
Both ways are correct, yes. Yeah, both ways are accurate. I'm gonna erase that because that's kind of sloppy looking. But you got the point, yes?
Yes, thank you.
Okay, all right, no problem. All right, other questions? All right, let's go up to, because we've been talking about configuration. And up top, that first example, it says draw the mirror image of each of the following compounds. And you can, let's work on that. Let's work on that. All right. And we'll do it with the plane. So I'll do, let's see, I gotta clear this off, shucks. All right, let's go here, right? We want to take that and draw the mirror image. This is what is this depiction called? This very first structure. What do we call that? Anybody?
The Newman projection.
Fisher.
Fisher projection.
Fisher.
Good. That's okay. We'll take it. It is a projection, so I feel you. So let's do this. Let's take this and boom, let's put a mirror plane here and let's have it look at itself in the mirror, right? What is that top atom? Would it look like this? Is that right? And then it's going to see, Br is going to see itself. Iodine is going to see itself. There's a hydrogen here. There is an OH here and an H here. Is that right?
Yes.
So anytime you're asked to draw a mirror image, you can do it this way, or you can just invert all the stereo centers and just write it that way. Here, this is a common a common trap, right? When you write the mirror image out, very common mistake is to change the stereo centers in the mirror image if you draw it as a reflection. Don't do that. Right? So this is going to see itself. Right? It will not see itself on a dash. It'll see itself as just like when you look in the mirror and you see your nose is pointing in the same direction. It's not on the back of your head. It's still in the same place on your face when you look at yourself in the mirror. So when you draw it this way with a mirror plane and a reflection, right, you just keep everything how it is. Like that, like so. Does that make sense? All right. Now, how do I know that that's right? If I took this molecule right here and I rotated it in space so that I lined up all the atoms in both isomers, what would happen to each one of those stereo centers if I turn this thing over and try to lay it on top of the original image? What would happen?
It wouldn't be the same.
Wouldn't be the same. The wedge would become a dash, wouldn't it? If I turned it over.
Right.
Now keep in mind, I'm talking about like putting a rotisserie skewer through here and just rotating the whole molecule in space, turning it over. Everything that's pointed out is going to now, when I flip it over, it'll be pointed back one. Is that right? Or did I lose you?
Makes sense.
Hmm?
It's hard.
It's hard to see in 3D. Think about it. Okay, I want you to do an exercise real quick. I want you to stand up and put your arms out in front of you, facing the screen. Let me know when you've done it.
Yeah.
All right? Are you up?
Yeah.
Now, I want you to turn away from the screen and put your back to the screen, but keep your arms out. What happened to your arms? Are they still facing the screen?
No.
They're facing the opposite direction, aren't they?
Yeah.
That's exactly what will happen with these theories. Because keep in mind, these chiral centers have a direction, right? They got a 3D orientation. So if the chlorine is coming out of the screen, when I flip that isomer over, that bond is not going to change. It's just going to be it's going to be pointed in the opposite direction now. Right? I'm not breaking bonds. I'm not detaching atoms. I'm just rotating this thing in space. Does that make sense?
Yes.
Hmm? All right. What about we got 10 minutes left? I'll only take 5. What about the last one? The mirror image for the last one. Can somebody do that? Able to annotate on your end? If you're on the phone, you may not be able to, but if you're on a computer, you may be able to. I have to change the security settings. Hold up. Let's see. Yeah, okay, I see you. I see you, whoever you are with the red pen. Go ahead.
All right. I don't feel like I have enough room.
Hmm?
But I don't feel like I have enough room. But
Okay, hold up. Let me zoom it out. What about now? Is that better?
yeah,
Oh, let me clear my stuff off too. Sorry. So, all right, go ahead.
mm,
Okay. Okay. Good.
that's supposed to be wedge. I mean, yeah,
A wedge. Okay.
oh goodness.
It is harder than it looks, isn't it?
Yeah, yeah, that's a dash.
Shout out to teachers.
Ooh, this is terrible, but yeah.
That's all right. I'm gonna redraw it. I think I understand what you're saying though. I see it. All right. Let- Yeah, it's harder than it looks. All right. So let me do some interpretation. So you put a mirror plane, and I'm gonna clear that out. Thank you for that. I see you though. I do see you. Uh, you put a mirror plane here. Is that right?
Right.
Hmm. And then I saw you draw this first, which is good. Yeah. And then this. Is that right?
Mm-hmm.
And the nitrile, and then the carbonyl, like that. All right. Good. All right. Let's do one more on number 2, where it says give the configuration. I'll let you work on the second and third one. I want to touch on the first one because we haven't done configurations on Fisher projections yet. So I want to talk about that for 1 second. If you watch the video for the Fisher projections, then this should not be Chinese or Greek, right? What is it about Fisher projections that we need to remember? There's one rule we need to remember because everything else is the same. Prioritizing, counterclockwise, clockwise, none of that changes. What's the one rule we need to remember?
The
It says
hydrogen has to
horizontal.
be vertical.
Look to determine if hydrogen is vertical or horizontal. Is that right?
Yeah, it's
Because
horizontally coming to you.
yes, so horizontal in a Fisher projection, the horizontal lines are actually wedged, and then the vertical lines are actually dashed, right? So in the other examples, when we had a hydrogen on a wedge, what do we do? Anybody remember the shortcut?
Reverse the rotation.
Reverse the configuration, whatever it is, right? Same here. So let's look at, there are 2 stereo centers here. Here and here, right? Let's look at it. Let's look at the top one. That's CO2H. That's an abbreviation for carboxylic acid. Y'all remember that functional group from part 1? Please, 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 let me just throw this in here. Functional groups do not go away. You cannot forget them. You're going to see them from now until December. So please refresh yourself on those functional groups. You can't live without them. You can't live without them. All right. So let's prioritize that. We know that hydrogen is 4 because that's always your lowest priority group, unless there's a lone pair present. And then my other groups are carbon right here, carbon right here, bromine right here. So of those three groups, which one is highest in priority? We know hydrogen is lowest.
Bromine.
Bromine. So that's going to be 1. And then of the two carbons, right, you have carbon bonded to oxygen, and you have carbon bonded to iodine. Which one is higher, do you think? Don't count the number of bonds to oxygen unless you're comparing two carbons that are both bonded to oxygen, right? So which one is higher?
The iodine.
Iodine. So this whole bottom piece is going to be 2. And then up top, that carbon is going to be 3. Are y'all following that? Is that clockwise or counterclockwise? If I count it to 3,
Counterclockwise.
it's counterclockwise, isn't it? Oh, is it? That's
Oh wait, no,
clockwise.
that's clockwise.
Yeah, that's clockwise.
Yeah.
My bad. I was just happy that somebody said it. All right. So it's clockwise. But what's the catch? On that stereo center, hydrogen is on a horizontal line or on a wedge. So you got to reverse it. So rather than it being R, it's going to be what?
S.
Mm-hmm. I had this little saying when I used to teach this. If it's going to hell, that means it's horizontal. If it's going to hell, change it. If it's vertical, it's going to heaven, keep it. But we ain't gonna get into that. But it may stick. All right. Let's do the bottom stereo center. All right. Go ahead.
Could you real quick tell me what did you say about when you're comparing the carbons, not to
Oh, yeah,
count
sure. Yeah, so when I'm comparing this carbon, when I'm comparing this carbon and this carbon, it's tempting to look at that carbon up top with it being bonded to oxygen 3 times and saying, oh, it's higher in priority. But the fact that the bottom carbon is bonded to iodine, right? It doesn't matter how many times that top carbon is bound to oxygen. Now, if that was in an iodine here, right? And it was just a hydroxyl, so I could say, okay, carbon, and then oxygen up top. Then I would count and say, okay, the bottom carbon is bound to oxygen once, top carbon bound 3 times, so that's higher in priority. But because of that iodine, I don't have to do that. Does that answer it?
Yes.
Hmm.
Thank
All right. Yeah, you're welcome. Good question. All right. So down on this carbon, that chiral center, iodine is 1, right? We have a oxygen and a carbon. So oxygen is obviously going to be 2, right? And then for that carbon, there's going to be 3. Anybody not see that? All right. Now, question is that clockwise or counterclockwise? And what's the catch?
Is it counterclockwise?
It
Oh
is.
no, it's clockwise. It's clockwise. I'm tripping.
Yeah, clockwise. My bad. I'm tripping too. Okay. Is H okay how it is? It's vertical.
It
Is that
should be
right?
good.
So we keep it. If it's vertical, we keep it. So if it's clockwise, that means it's going to be R. All right. I know we got to go. I said I was going to stop at 9:55, but touchscreen got me. Kept me excited the whole time. All right. Any questions about the Fisher projection?